Right. Good afternoon, good evening, and for some people, good morning, and welcome to the fifth day of the Tommy Flowers Network conferences. For those of you that were with us yesterday, it was all about quantum, and today we're going to shift gears slightly and get into data science and artificial intelligence. I'm Mike Williams. I'll be acting as your moderator throughout most of the session, not all of it, but most of it. And also, can I ask anybody who's not speaking to please either to mute your microphones and to also turn your cameras off. It just makes the focus on the screens a lot simpler from that perspective. So the first person I'd like to introduce is Fraser Burton. Fraser is the host and sponsor for these events throughout the week, and Fraser is also the senior manager of network physics within BT's Applied Research Department. So Fraser, over to you.
Excellent. Thanks, Mike, and welcome everyone. This is the final day of the 2020 Tommy Flowers Network Conference, which we're calling Let's Get Physical. It has been a fantastically successful week, so thank you to everybody involved. If you've missed any of the days, then they will be, they have all been recorded, so you can catch up later. As Mike said, I am Fraser Burton, and I lead BT's Network Physics Research Team, and I've been the host for this week. This is the fourth year we've been running these conferences, and I'm delighted to say that we have had more attendees for this event than ever before. Now, I know why that is. It's because it's online and it's a lot easier to attend. But what that does underline is that the last 6 months have been, last 7 months actually, have been really difficult with the pandemic, and the vast majority of us, certainly those of us here on the call, will have been working from home pretty much exclusively. And just 10 years ago, that would have been pretty much impossible. Well, it would have been possible, but we'd have been on the phone and reading books, and the quality of interaction just wouldn't have been up to the grade it is nowadays. And that really does underline, I think, the societal impact that telecommunications has, and how that will only grow as we go forward, I think. Which really underlines the importance of the Tommy Flowers Network. So the Tommy Flowers Network exists to bring together the communications and IT industry, together with academia, both in the UK and globally. And our purpose is to develop the skills and the knowledge base of our future research leaders. So that's our present postgraduate researchers and undergraduates as well. It's worth saying a few words about who Tommy Flowers was. He's not really a household name, which is a shame. Tommy Flowers was a wartime communications engineer. He worked for the General Post Office, as it was called in those days, which was a predecessor organization to what became BT. And he was working on the use of electronic valves in telephone exchanges. And it turned out that he saw that the use of valves could be applied to automating the code-breaking algorithms which were being developed at the University of Cambridge. So he worked alongside the likes of Alan Turing, who is a household name, and his work and his team resulted in the development of the world's first electronic programmable computer, which was called Colossus. The world didn't know he'd done that at the time because the work was protected under the Official Secrets Act, but that's what he did. And Tommy is one of our heroes because he is an excellent example of how industry and the knowledge of practical applications can work with academia, who are really kind of pushing forward the boundaries of knowledge, and they can come together to make a really significant impact on society. And that's really what we aspire to with the Tommy Flowers Network. So throughout this week, we have lined up some really top quality presenters from across both industry and academia. and we've had world-class experts in each of the topics that we've been exploring each day. We've had some very lively discussions. I hope we will today. And there are plenty of opportunities for you to ask your questions. Please don't hold back from going into the chat and firing those questions into us. Okay, so this is our fifth and final day of the conference, and we are focusing on the role of data science and AI techniques applied to physics and telecommunications. And we're focusing in on the lives and the achievements of physicists and engineers who are using this very new science to extend the capabilities both of fundamental physics and also communications. So later today, we have Dr. Detlef Nauck, who is head of AI and data science research at BT. And he's really going to be going deep into data science and AI techniques. And he'll be joined by guests from academia and industry. But in the interest of time, I'll leave those introductions to Detlef when we get there. But right now, I am really absolutely delighted that our keynote speaker is Professor Jesse Thaler from the Massachusetts Institute of Technology. Jesse is Associate Professor of Physics, and also he is the newly announced Director for the National Science Foundation's AI Institute for Artificial Intelligence and Fundamental Interactions. Now, this is one of the inaugural NSF AI Research Institutes, so this is a pretty big deal, guys. So I'll stop gushing, and I am now delighted to hand over to our keynote speaker, Professor Jesse Thaler.
Thank you so much, Fraser, for the introduction, and thank you to the Tommy Flowers Network for inviting me here to speak. And this is a fortuitous collision of the world of physics and the world of data science and artificial intelligence, and kind of amazing that this NSF AI Institute was announced precisely at a time when it's relevant for me to come and speak to you all today. So I'm going to be talking about artificial intelligence and fundamental physics, but first let me advertise this new AI Institute funded by the NSF. And you can see here our logo, which, depending on how you read it, is either a capital A with a lowercase I on top of it, or the letters FI. And what we see is that artificial intelligence in our minds and fundamental interactions are truly intertwined. And for any of you in the audience who are interested in continuing research in this area and you're entering into your postdoctoral stage, on October 20th is the deadline for a postdoctoral fellowship opportunity to apply to be one of the first I-FI fellows. So we're calling our institute I-FI, kind of shortening of artificial intelligence and fundamental interactions, I-FI. And if you go to ifi.org/fellows.html, that's an opportunity for you to apply to our program. So let me say a little bit about fundamental interactions. For those of you who don't know, a vast fraction of the universe we actually understand by two pillars of fundamental physics. One is Big Bang cosmology, and this explains how the universe started off in a hot, dense state and then expanded under the influence of gravity, dark matter, dark energy, and radiation to become the cold place that we inhabit right now. That's not going to be what I'm going to be talking about today. I'm going to be talking about the other scale, the shortest distance scales in nature, which are described to the best of our knowledge by the standard model of particle physics. And in this kind of pie chart, you can see all of the fundamental particles, in orange, the quarks, in green, the leptons, in blue, the force carriers, and at the center of the standard model, the Higgs boson. And I'll be telling you a little bit more about the standard model momentarily. But the thing I want to emphasize here is that these are the pillars of our understanding of fundamental physics, and they're triumphs of human intelligence. And triumphs of the experimental method, the scientific method rather, where you can combine experimental results, observation, theoretical calculations to really understand the fundamental structure of the universe. And kind of colloquially, we talk about the four fundamental forces: gravity, electromagnetism, the strong force, and the weak force, and the way that they shape our universe. And as you'll see in this talk, the strong force is going to play a particularly important role. So I said that this is a triumph of human intelligence and a triumph of the scientific method. And what we'd like to do is we'd like to translate these successes into the world of artificial intelligence, as well as benefit from artificial intelligence to push the frontiers of knowledge. Since while Big Bang cosmology and the Standard Model describe a lot of known physics, it doesn't describe everything. And so we keep on pushing into the frontiers of discovery. So the title of my talk, I gave it as Collision Course, and I mean collision course in two ways. So one, I'm going to try to teach you a little bit about particle physics. And what we do in particle physics is we slam together particles, study the debris, and somehow figure out the nature of the universe. Here, this is an image from the CMS detector at the Large Hadron Collider outside of Geneva in Switzerland. And here we're slamming together protons. Maybe we're creating some new state of matter or some new dynamics that we'd like to understand. Maybe we're seeing just the results of the Standard Model of particle physics. Whatever it is, the collision debris we need to interpret and do inference tasks to figure out what's going on. Now, I'm also calling this talk Collision Course for another reason, because in my research, but I think more in the community generally, there's been a collision between two different broad fields, the field of physical sciences and the fields of mathematics, statistics, and computer science. And it's been quite remarkable to me in my research to realize that some of the questions that I'm asking in fundamental physics turn out to have analogs in the broader mathematics, statistics, and computer science world, or maybe under a larger banner, the banner of artificial intelligence. And part of the motivation for this new NSF Institute for Artificial Intelligence and Fundamental Interactions is that we think that we can advance physics knowledge from the smallest building blocks of nature to the largest structures in the universe, and galvanize AI research innovation at the same time. And in fact, we see great synergy between these programs. So what I'm going to be talking about today as my example is an example of trying to teach a machine to think like a physicist. So what do I mean think like a physicist? We teach our first-year students at MIT about mechanics and about electricity and magnetism, but we also teach them how to check their answers to verify their solutions, teach them about dimensional analysis, other strategies for problem solving, and we'd like to incorporate those into machine learning architectures. And this is maybe in contrast to trying to teach a machine to think like a child. I mean, the childlike creativity is wonderful, but I don't know about you, but trying to reason with a toddler for me is quite challenging. We want to have AI techniques that can actually, in some sense, tell us what they've learned and have the ability to verify their results. And physics is one domain where that's especially important. So when I first thought about whether you could teach a machine to think like a physicist, I thought, I'm not sure this is so possible because, what is the machine doing? This is an example of one of the triumphs of deep learning technologies. This is what's called an in-painting task, where you take the image on the left-hand side, where you've masked out pieces of this library, and then you try to predict what the other side, or what's behind the mask. And so on the other side, on the right-hand side, you can see a wonderfully reconstructed rendering of a library. And the standard lore about what's going on here is that this is the deep learning revolution, the revolution of what happens when you have gigantically large data sets, increased computational power. And if you have that, then basically if you've seen 1 billion bookshelves, you've seen them all. And that's why you're able to do this reconstruction task by taking the prior information from your vast database of images and using that to infill the image. But what's remarkable about this particular example is that's not what's going on here. In fact, this is an AI algorithm that's never seen another picture of a library. Instead, these researchers understood the structure of the problem and how you basically capture repeating patterns in a machine learning architecture, even if you've never seen exactly what those repeating patterns are. And so I'd like to think about this as deep learning meeting deep thinking. Deep thinking about the structure of the problem allows us to find more successful solutions. So in my research, I know a lot about the structure of my problem. I'm a theoretical particle physicist, so I understand the structure of the Standard Model, and I'll try to give you a little bit of a particle physics 101 right now. So here's all the fundamental particles in nature, and this turns out to be not at all what you see when you slam together collision debris. Most of these particles are unstable. They are very short-lived. You don't see them directly, so you have to just infer their presence. What you do see is you see some of the particles that experience the electromagnetic interactions. So you see the photon, the muon, and the electron. But then the quarks and gluons of the Standard Model, you don't see them directly. Rather, you see bound composite states, bound by the strong force, And you have to infer from the pattern of these composite states as well as the smattering of elementary states what's going on and trying to reconstruct the standard model from the debris that you see in the collision. And as a data science task, this is a fascinating one. So here's an example of a collider event. And you see these, to my mind, beautiful sprays of patterns coming from the collision point. And you can think about these as being points in momentum space. Each one of these orange lines, which connects to a green box, which connects to a blue box, that is an example of a particle trajectory that has momentum in the x, y, and the z direction. And so we have momentum in 3 dimensions. And we want to take this bundle of particles going all over the place, let's say hundreds or thousands of particles coming from the collision point, and we want to understand what their origin is. And to do that, we have to do a massive inference problem. And when I say a massive inference problem, that massive part is because you don't just see one event like this. You see every 25 nanoseconds, collisions are happening. And so that's 40 megahertz data rate where the pictures that you're taking are roughly like a 10 megapixel camera. And that's an enormous data volume and a challenging inference task. But this is a challenging inference task that actually looks very similar to one where you might have encountered it just more broadly in society. That here we're talking about a collection of points in momentum space. That's a collider event. But thinking about collections of points in position space is what's known as point cloud learning, famously in the context of LiDAR point detectors for self-driving cars. And here we have a bunch of points not in 3-dimensional momentum space, but in 3-dimensional position space. And a lot of the tasks that we want to do are very similar to the ones in the collider physics context. So, for example, we'd like to identify objects. Those are these pink and blue boxes. Well, in particle physics, we want to identify clusters of particles. And in my field of research, those are called jets. So trying to identify interesting clusters of objects in my event. In the jet physics context, we'd like to tell the difference between sprays of particles coming from difference of the fundamental particles. So sprays of jets that originated as quarks or originated as gluons. Well, that classification task has a mirroring in, of course, self-driving cars and telling the difference between a car versus a bicycle versus a pedestrian. And more generally, there's plenty of other tasks that are mirrored between the fields. For example, noise removal is one. Robust treatment of outliers is another. And so what you might think is we could just take all the off-the-shelf AI technology that's been developed for self-driving cars and just apply that in the particle physics context. But that's not taking advantage of thinking like a physicist. That's not taking advantage of the domain knowledge that we already know and the strategies that we've already developed to analyzing our data set. And so we want to import information from physics to build our AI techniques. And so I'm going to try to explain the dynamics of jet formation. So this is the type of thing where people take entire courses at the graduate level on this. But let me try in one slide to explain how jets are formed. And again, this is the dynamics of the strong nuclear force. So we slam together protons, and we're able to probe via very high energy collisions, very short distance physics. And at short distances, the dynamics of the standard model involves quarks and gluons, and that's what's created in the collision point. But because the strong force is strong, it ends up binding those quarks and gluons together to form composite states that are known as hadrons. The proton is one example of a hadron. Other names of hadrons are pions and kaons. Those hadrons hit your detector, and you have to reconstruct by your experimental detector what happens, and different ones of those composite hadrons leave different signatures in your detection. And as you can imagine, this is a complicated generative model for jet formation and a complicated inference task if you want to take the detected signals and reconstruct the quarks and gluons that you made in the first place. But what we have is we have domain knowledge about the field of jet formation. And as a theoretical physicist, the way that I think about jet formation is by something a little bit simpler. So in theory land, what I think about is I think about a quantum mechanical operator. So I guess yesterday there was a discussion of quantumness. A quantum mechanical operator called the energy flow operator. And for those of you who know something about general relativity, the capital T in this equation here is the stress energy tensor. And basically the energy flow captures the flow of energy from the collision point off to infinity. And that information about energy flow, in part because energy is a conserved quantity, that information about energy flow is robust to hadronization effects, robust to detection effects, and gives us our closest glimpse of quarks and gluons. And so if I used naive off-the-shelf machine learning techniques, they wouldn't know about this energy flow concept, and therefore they would not take advantage of our domain knowledge. But what we can do is we can bake in this energy flow concept, we can bake it into our technologies. And in doing so, we can do better tasks for particle physics. And what's interesting is that this notion of energy flow actually has analogs in other areas. And if people are interested more in that in the Q&A after my talk, I'm happy to discuss other applications where this idea of energy flow or its generalization appears in the physical sciences. Okay, so this is the most technical part of my slide, of my talk rather, the most technical slide of my talk. And so what we have on the one hand is we have a principle of fundamental physics. This is the robustness of energy flow. And this is a concept that comes from quantum field theory. I've tried to simplify it as much as I can, but it's a pretty foundational idea in the way that we do particle physics calculations. On the other side, we have the power of artificial intelligence, and in particular, a huge literature on point cloud learning. And the particular technique I'm talking about today is related to technologies developed by at Carnegie Mellon University, a technique called deep sets for point cloud learning. So we take a principle from fundamental physics, the power of artificial intelligence, we slam them together, and what happens? Well, it turns out you need more ingredients than just that. You need two spectacular graduate students, Patrick Kamitsky and Eric Metodiev. You need funding to do this kind of research, and so, of course, the NSF is supporting the AI Institute, but I'm also supported by the Department of Energy and the Science Foundation, the Simons Foundation. And you also need cloud computing resources in order to carry out these calculations. So we benefited from Microsoft Azure, Google Cloud, as well as the MIT Quest for Intelligence for doing this research. And then finally, when you put all that those ingredients together, out pops a website, or out pops a pip installable package of energy flow networks. You can click here at energyflow.network, and this is the work that Patrick, Eric, and I did to bake into a machine learning architecture this principle of energy flow that comes from quantum field theory. Okay, so I don't know if you can see very clearly this little picture of the website, but maybe you see this kind of colorful image that I'm going to blow up and try to explain to you. Okay, so what do we have here? And what you're going to see is a bit psychedelic, and I'm going to try to explain to you what this image is. So this is the machine-learned representation of a pretty foundational principle in quantum field theory, but also for understanding the strong force. Okay, so what you're looking at is how the machine is paying attention to information when it's given an example of a jet. So just to remind you, we have collisions at the LHC. We have to identify clusters of objects. Those are called jets. And then here what I'm doing is I'm taking that jet and orienting it such that the jet is flowing its energy into the slide. So this is like shining the jet on a camera. And here I'm taking a picture of that. So the center of the image is the center of the jet. And then these rings, you should think about these rings as being filled in. And these rings, there's 256 of them. That's one of the hyperparameters of the AI algorithm, is how many of these, what's called a latent space dimension you have. So this is a latent space of 256 dimensional. And inside these rings is showing you essentially where the algorithm is paying attention. And what you see is that the algorithm is paying attention to the periphery with these large rings. And then as you go closer and closer to the center, you get smaller and smaller rings. You see that these rings are distributed symmetrically around the central point. So if you do a rotation in the 2D plane, the rings are oriented symmetrically. There's many, many rings, but as you rotate, they kind of map onto each other. And that captures what's known as an azimuthal symmetry of jets. And then if you just stare at this, you stare at this long enough, you realize that the ring patterns are self-similar as you go towards the center. There's like a fractal-like behavior where the outside rings are large, the inside rings are smaller, but there's a particular scaling exponent that tells you how you go from the large rings to the small rings. And remarkably, this scaling exponent is one of the things that we teach students who study the strong interaction, the scaling exponent that you expect for the strong force. And indeed, that scaling, or more accurately, the breaking of that scaling, was the reason for a Nobel Prize in 2004 for understanding the strong interaction. And if we had a perfectly scale invariant theory, we wouldn't have a very interesting universe to inhabit. But because the strong force gets strong and there's a violation of that scaling symmetry, that's actually what triggers this hadronization step, the strong force getting strong and binding things together. And so if I really went to the very, very, very center of this image, you would find that the ring stopped growing stopped shrinking, and they started getting to a fixed value corresponding to the confinement scale, what we call, of the strong force. Okay, so that's pretty cool. And let me just try to just give you a little bit more detail. So here, the way that we've trained our neural network is via what I'll call the hello world of jet physics, a very simple binary classification problem of telling the difference between quark jets and gluon jets. The algorithm that we're using is an energy flow network, and so I'm not showing you the neural network diagram for that. That's buried in this f and the phi function. But what I want to emphasize is that we're doing the specific energy flow restriction, where in green you see energy as appearing in a linear way, and that turns out to be a way of encoding this complicated quantum field theory principle. Actually has a pretty simple representation in terms of a neural network architecture. And then this strategy for verification that I'm showing you here, again, the network has learned to tell the difference between quarks and gluons, but I can verify that the network is using trustable information by going inside this latent space, which is labeled here by these V functions. And now I have a strategy for verification, able to see what each latent space dimension is doing. And remarkably, they've organized themselves in terms of the fractal structure of the strong force. So we succeeded in this context. We taught a machine to think like a physicist, or rather, we encoded a particular physical principle into the machine, and in return, the machine learned something that otherwise I would have to take a quantum field theory class to learn about. And you can imagine not knowing the dynamics of the strong force, you could have done this and then realized that you have this fractal self-similarity. It's remarkable that the machine learned the fractal structure of the strong force. That wasn't obvious at the outset. But now we have a cycle where now we've realized it can take this knowledge, we can bake that knowledge back in and see what other types of discoveries we might make, and potentially even discover things that we didn't already know about. In this case, I already knew about the fractal structure of the strong force. What we're really excited is applying this to cases where we don't know what the answer might be. And so kind of zooming back out a bit to this new NSF Institute for Artificial Intelligence and Fundamental Interactions, our institute sees many fascinating ways that there can be intersections between techniques in artificial intelligence and fundamental physics questions. And what unites all of these questions, despite appearances, despite that these graphics that I'm showing you on the slide are very different, they all involve data-rich science. Gravitational waves, a triumph of both the theory of general relativity, but then also the ability to build exquisite interferometers to see the minute ripples in space-time that allows us to infer that black holes form binary pairs that then spiral into and give rise to this gravitational wave explosion. That's a data-rich area, and techniques of AI we think can improve there. In nuclear physics, in particular in theoretical nuclear physics deals with trying to understand the strong force in more detail. And there you have synthetic data, created on a computer that then you want to sift through in order to understand how nuclear physics interactions work. In astrophysics, we've entered the era of multi-messenger astrophysics, where we have multiple ways of looking at the universe, both in optical, in neutrinos and gravitational waves, radio. And synthesizing that data is a challenge at the intersection of artificial intelligence and fundamental physics. I already gave you an example of particle colliders. Let me turn to mathematical physics. Here, there's fascinating questions coming out of string theory that we can answer using AI techniques, where there's certain knot-like structures that actually underpin our understanding of the shortest distances in nature, and trying to unravel those knots is something that we can do with AI. And then finally, dark matter. This is a mysterious substance that's actually 5 times more abundant than anything that I showed you in the standard model. It's absolutely important for the growth of structure in our universe, but we don't know much about it. And understanding both its gravitational behavior, but also its potential behavior under other forces, is something that we think we can do at the intersection of artificial intelligence and fundamental interactions. And so what I want to leave you with is I want to leave you with a question, and hopefully this question will spark questions to me, of what principles and strategies from physics could you incorporate into your research in data science and AI? And I'm coming from the perspective of fundamental physics, and of course physics is baked into the DNA of the research that I'm doing. But strategies that we teach in physics classes are relevant well beyond the physics domain. And I gave you an example of a few of those principles and strategies in this talk today. So I told you about this energy flow concept, which is an example of a symmetry. or the scaling symmetry. That's an example of a symmetry, and how can we bake symmetries into neural network architectures. And then I talked about verifiability, the ability to actually peer inside the network and actually find ingredients that you can test. And we do this all the time in physics calculations and in physics experiments. We do beam tests in collider physics. And what types of verifiability strategies can you bake into your AI techniques? Many other concepts from physics that might be relevant. And with that, let me close out, and I look forward to getting your questions about this fascinating intersection between AI and fundamental physics. Thanks so much.
Great, Jesse. Thank you very much. We do have some questions coming in at the end of the day. So the first one is understanding the decisions made by an AI system can be a challenge for humans. So when an AI is trained to think like a physicist, how can we understand the insights that the AI gains about the universe?
Yeah, so one of the ways that we structure physics problems is that we make sure that we have intermediate steps along the way where we can check and cross-check. And I do this all the time with my graduate students. My graduate students will do a very complicated calculation, and they'll hand me 10 pages of notes. But what I ask to see is not the intricate details from that full 10 pages, but just the key stepping stones along the way. And so the strategy that we have been pursuing in our research is to make sure that there's intermediate steps or auxiliary outputs to the neural network that we can check, such that even if the specifics of how the AI is making a decision is opaque, the bigger picture about the broad information that's used is apparent to us. And so that's one strategy that we are using to try to have the machine, in some sense, talk the same language that physicists do.
Great. Thank you very much. We've had another question. I know your focus isn't on cosmology, but do you feel AI techniques have anything to offer in terms of dark matter and dark energy investigations?
Yeah, I think there's incredible opportunities there, and there are two different aspects of it where I see opportunities. So one is just on the data science side, that particle physics deals with massive amounts of data, but now with next generation observatories, we have the same type of data volume challenges in cosmology. And so just from a data processing and a data analysis strategy, there I see enormous opportunities. But on the more kind of fundamental side, what's maybe not so well known is that cosmology, we can understand the evolution of the universe, but partly why we can do it is that cosmology is in what's called the linear regime, basically where linear differential equations can be used in order to understand what's going on. And once you get into the nonlinear regime, then you start to get into really fascinating computational challenges. And so just predicting what's going to happen when you, in a computer, start simulations is a challenge. And so what we see opportunities to do is actually to do better numerical simulations of gravitational interactions, such that we can actually track into the nonlinear regime the growth of structure in the universe. And that's one of the key questions that we like to understand is cosmology, that detailed pattern of growth. And we think we can tackle that with the help of AI.
Great. No, thank you very much. Anna Khan has asked a question as well. So do driverless cars differentiate between cars, humans, and bicycles by looking at the energy off of them?
Good. So this is well outside of my expertise. My understanding of these LiDAR point detectors is that they're detecting points in space, and I'm not sure what type of energy or frequency information is encoded there. But the energy flow concept that I was talking about in physics, that is the best analog of something like a photon intensity with a camera. So the energy flow is basically like taking a picture. To taking a picture in energy directly as opposed to taking a picture in terms of light. And so I think that's where the analogy is, that the LiDAR point detector is seeing essentially light bouncing off, laser light LiDAR, and in the particle physics context, the particle physics detectors are seeing the flow of energy deposited in what's known as a calorimeter.
Great, thank you. And I've been waiting for this question to come up, but because it's always inevitable when you talk about AI, that if we train AI with incorrect assumptions about fundamental physics, it may draw incorrect inferences. So is there a way to minimize any bias we may add?
Yeah, okay, so this is a great question. And in fact, this is why it took me such a long time to embrace artificial intelligence as a research strategy. And for a long time, I was going around and kind of making fun of the deep learning revolution and saying, I'm a theoretical physicist, so what I prefer to do is, my deep thinking. And so use that deep learning versus deep thinking as opposites in some sense. And what changed my mind was realizing that this question about how you make essentially AI not subject to human biases, that itself could be phrased in a well-posed way, that there was a way of building AI techniques that in some sense knew about human biases and could find a way to counteract that. So in particular, the best way to avoid human biases is not to use any data that's been synthetically generated using human priors, and instead analyze data directly. And so I can imagine taking the raw data from the LHC, and instead of training an AI technique on synthetic data that I've created on my computer, I could just try to train it directly on the data from the LHC. And this would be equivalent to like saying, I'm not going to teach a self-driving car anything about humans versus bicycles versus pedestrians. All I'm going to do is just give it data, raw data, and say, hey, you figure out that there's categories of objects with bicycle, human, and car, that basically you use the data itself to identify categories. And I thought this was crazy. How could you possibly do that? Until I realized that this is done in natural language processing all the time, that you basically can hand algorithms a stack of documents and say, here, build a card catalog out of this, build a categorization of all these documents into what topics they belong to. And this is a technique that's known as topic modeling in the natural language processing case. It's known as blind source separation in other contexts. And the realization that I could just take the data itself and let the data speak for itself and actually train AI on data that, in some sense, a human never labeled initially, that's what changed my mind. And in fact, I didn't say that, but the story that I just told you there is making use of that unsupervised or semi-supervised machine learning strategy in order to reach the inferences that it did.
Great, thank you. I actually witnessed a debate about this next question. Can we train an AI to challenge us and our science? So, for example, could an AI discover an alternative interpretation of fundamental physics other than ours, given the same inputs?
Yeah, it's a great question. And you can ask, could the history of our field have been different if we had AI in the driver's seat? And I have evidence that this is, in fact, true in my own subfield. So I said that my subfield deals with these collimated sprays of particles called jets. And in some forthcoming work that I'm doing with collaborators at UC Irvine, what we're trying to do is say, okay, let's take some of our domain knowledge of physics, bake it into an AI technique, and then remove that knowledge at some level and ask, okay, now AI, I've taught you what I know. Now can you re-go through the history of our subfield and say, what would you have discovered in what order? And it learns things in a different way. It learns different strategies that turn out to have the same efficacy for the problem at hand, but they're different, and they're different in interesting ways, that it used the information that we talked about physics, it used it in different ways than the human did. And so this would be fantastic if one was able to take collider physics data and realize that there was a totally different way of describing the dynamics. And maybe what I think of as being very complicated with the strong force turns out to be much simpler if there's an alternative explanation. I don't know how to build an AI technique that could do that at the moment, but I see potential strategies going forward that might be relevant in that direction.
Great, thank you. And kind of adjacent to that, I've got two questions I want to get to here. One was, Roger Penrose has just won the Nobel Prize for Physics. Is it ever possible that AI might win it one day?
Excellent. I'm glad someone mentioned that, because I had a backup slide talking about this fantastic discovery of supermassive black holes and Penrose's role in the theory of that. And this is just another example of theory meeting experimentation, meeting data science. But I think we have to be optimistic that when given the right initial information, that AI could make a discovery that was as transformative and potential Nobel Prize worthy. But I think we have to remember that these things don't happen in a vacuum, and everyone's work, both human and machine, builds off the previous generation. And President Rose's work is absolutely essential for understanding of black holes, but of course it builds on our understanding of gravity and other concepts going further back. And so even if AI ultimately has that creative burst, it will be the foundations of human intelligence that would have made that possible.
Great. No, thank you. Thank you very much. So I'm going to have to unfortunately bring this session to a close. I think we could have gone on for another half hour or so just with questions that's coming in. So thank you very much for that. So I need to move on to our next speaker now.
Thank you.
So I'd like to. So the next two sessions, we're going to get a kind of a commercial and industrial view of AI. Then we're going to move into a more academic view. So our next speaker is Dr. Detlef Nauck, who's the head of AI and data science research at BT. And so, Detlef, I'll just hand over to you.
Thank you, Mike. Hi, everyone. I want to talk a little bit about how we do data science and AI at BT and what the particular challenges are for doing this in a large organization with a kind of a commercial perspective, and how we do this from an organizational perspective. So it was a very fascinating talk by Jesse, and I immediately thought if we can build kind of constraints into AI models like symmetry, that would be really cool. So I think we have a lot to learn from this field, and how we can apply this in our kind of more mundane everyday data science and AI at BT. We have a long history of working with AI at BT. We have a 25-year track record of research and adoption by the business. We actually have the largest AI patent portfolio in the UK, and not a lot of people know this. So we have always worked in this field, and a lot of solutions that are now in use in BT have come out of this research program. So just a few examples that have come out of the program. So we're using a lot of AI in cybersecurity, where we use intelligent visualization to point cybersecurity experts to potentially suspicious patterns in network traffic. The mobile workforce that BT has, around about 30,000 engineers who drive in their vans to locations to deliver broadband or repair faults. This workforce is managed by an AI system, and this would be one of the kind of more classical systems that use optimization and search, not so much the kind of modern algorithms like deep networks that you hear a lot about these days. And this system is been used for over a decade, and we are expanding it, and we are now looking into giving augmented reality to our engineers, where we then use things like image recognition. So you look at a piece of hardware that you have to fix, and the system picks this up through your augmented reality glasses, tells you which part it is, and pulls up information that helps you fix it. We use it for network planning, again, search and optimization strategies that help us to deploy new networks faster than ever before. We use data science to detect nuisance calls through anomaly detection and calling patterns and block nuisance calls. Machine learning is used at scale in marketing operations. So when we send information to customers about products and services, this is based on scoring algorithms that we use, what people might be interested in. And we are using natural language processing and sentiment analysis to engage with customers through social networks. When you have this challenge of rolling out something like AI or data science in a large organization, then you very quickly realize that there's what's called a hierarchy of needs. So you cannot just start and say, okay, I want to use a fancy AI algorithm, a deep network or something like this, without having some foundation in place. And a lot of organizations have realized this and struggled with it, because the development towards these kind of techniques is not straightforward. The kind of use of data in operational systems has always been done with the kind of purpose in mind of supporting an operational system, like billing, for example, or taking orders. And only over the years, people realize there's so much value in data. If you can bring it together and analyze it properly, you can support decision-making in large organizations and become much more effective. But in order to do this, you need to be able to collect data. You need to be able to put it in place. You need to store it and move it about, and you need to be able to transform it and clean it. And you need to have the right labels against it, so you can create training data that you can then use to teach machine learning algorithms to develop good solutions. And when you can do these things, then you can go into things like AI and deep learning. But if you don't have this in place, then you build this whole stack for each application. So it's really important to have this kind of hierarchy in place. And there's another important thing about how you go about building machine learning models and use them in operation. And this links back to the scientific method and ideas like reproducibility. So when you build a model from data that you want to use to make decisions in your operational landscape, be it to market to customers or to detect faults in your network or to send engineers to the right job, you need to know that what you put in place does the right job and does it correctly. And there's a whole kind of workflow that you have to put in place that starts somewhere in a data repository where you collect your data. And then you have to beat the data into shape. We call this data wrangling. And you generate features which you then use in a machine learning algorithm to build a model. And then you deploy this model and you apply it and you make decisions. And this whole chain basically culminates in this decision making, which obviously you want to be correct. So you want to make correct decisions and you want to get business value out of this decision making. So it's not just about are the decisions correct or not, but how much value do I get out of this decision making? Or have I built something that makes decisions that don't make me any money? And in order to get this right, you can look to software engineering and how they build software. And central to the idea of software engineering these days is testing. So you at every step of the way, you test what you do and you try and figure out if the software is doing the right thing. And you can apply these kind of ideas in machine learning workflows as well. You can use ideas from software engineering to do versioning at every step and logging and figure out if you're doing the right thing. So we're working at putting these sorts of workflows in place, and this is called MLOps these days, machine learning operations. This is one of my favorite quotes, because what we do in machine learning is we build models, and we should remind ourselves that these models will always be wrong, and hopefully they are useful. So what we build in machine learning are statistical models. They're pretty much pattern recognizers, and they will never be 100% correct. They will have fallout and faults. And that means when we use them in practice, we need to understand what these faults could mean and how we mitigate against them. And this is particularly important when we make decisions that affect people. So that could be simple things like marketing, where you'd say, okay, the effect is not that great, but if you make decisions about giving out loans, or if you make decisions about which employee should take what sort of job in an operational setting, then you have to be careful and you have to understand what sort of mistakes might you make and how do you mitigate against them. And I just want to mention two areas of potential mistakes, and we will probably pick this up again in the forum later. But there's one strange aspect of complex AI systems, particularly neural networks. They like to cheat, and that means that they pick up artifacts in the data. And I'll show you an example in a minute. And so you think they have solved the problem that you trained them to solve. And even on the test data that you have, it looks all great. But when you then later deploy them in practice, it all falls apart. And then you find that what your network has actually done, it has focused on some artifact in the data that you didn't know exists. And one potential artifact can manifest itself as bias. And here's a recent example of an AI system used by the Home Office. And that was kind of hidden in the application. So the application is supposed to tell you if your passport photo that you are submitting in an online application qualifies as a passport photo. And it turns out that this system is badly biased against dark-skinned women. And in the whole kind of application, somewhere baked in sits a facial image recognition system. And if you have followed the news about discussions of AI, you know that facial image recognition systems have this bias very often because they are trained with the wrong type of data, and nobody has checked properly when releasing them if all types of faces can be equally well recognized. And so this is a particular problem if you put an AI system somewhere into your application and you're not aware how it has been built, who has built it, with what sort of data, how it has been tested. And so this then causes obviously all sorts of problems. And if you're not aware of these kind of issues from the beginning and you mitigate against them, then it basically jeopardizes your whole application. There's a lot of discussion around how can we make sure that AI systems do the right thing? Can they explain to us what they're doing? So there's this idea of explainability, and there are different reasons why you would want your AI system to be in a way transparent and interpretable, or being able to explain to you what it does. And so you would want this to know that you can trust it, that you have causality in the system, that you have used good science to do it. You want to be able to challenge outcome of decisions. If an AI system makes a decision about you and you feel it's wrong, you want to be able to challenge it. And you have to be able to ask the question, how do you come to make this decision? You want to learn from failure, obviously. And so you want to make sure that the same kind of mistake doesn't happen again, that you can somehow engineer it out of the system. You want to be sure that the system is behaving ethically and is fair, that it does not have bias baked in, either through training data or the way it has been engineered. And you have to follow legal and regulatory obligations. So if you make decisions about people, then the GDPR tells us that we have to explain to people how we came to this decision. And that can be very difficult if you use particular AI systems like deep networks, where you basically don't know how they came up with the output. Even if you get explanations from systems, they're not always helpful. So here's a comparison between human attention and where a deep network looks at a picture. So it's a deep network that was trained to answer questions about pictures. And so the top row, he says what's covering the windows, and the answer is blinds. And when you ask a human to answer this question and you track their attention, then you can see they're looking at the windows, while the AI system looks all over the place. For example, it looks at the lamp in the picture, which is not quite clear why that is. But it's clear from this sort of analysis that the AI system has picked up something completely different to what's actually the meaning of the picture or the question. And it looks at artifacts in the pictures that help it to make a decision and produce an output. But this is not necessarily what we are after. So this discussion around how do you trust AI systems? How do you make sure that they are being used in an ethical way? It's a discussion that has intensified over the last 2 years, and you find more and more frameworks that help you with this. And here's a kind of a surprising company that came up with a framework. It's Rolls-Royce. And what they do is they use neural networks to monitor airplane engines in flight. And you can imagine that if you use AI for this, you really want to make sure that the system does well and doesn't make mistakes. And out of this kind of idea of quality monitoring in AI system, you could also come to ethical considerations. And you kind of find if you build a high quality AI, it is easier to also make sure it behaves ethically.
Yeah, I've always had that thought process about, if AI is a black box, how do you know it made the right decision? But I think we're about to get into a debate about all of that here. So I'd like to bring back Detlef. We're going to get into a forum discussion and debate themed around how do we know that AI is actually doing the right thing? So Detlef, I'll just hand over to you to lead on that at this point. And if I have any questions come in, I'll try to get them to you.
Good. Thank you very much, Mike. So I would like to start with introducing our panelists. So we have MariaAxente, I hope I pronounce your last name correctly, Maria, from PwC. Maria is the lead for responsible AI and AI for good at PwC. And she's also a globally recognized AI ethics expert and a member of the advisory board of the UK government all-party parliamentary group on AI. Then we have Lorna McGregor, who just joined us in time. Hi, Lorna. Professor Lorna McGregor is working at Essex University. She is a professor at the law school and director of the Human Rights Center, and also runs a large ESRC grant on human rights, big data, and technology. And then we have also on the panel Professor Mike Locke, who has been introduced already. And I don't know, Jesse, is Jesse joining us as well? We had some. Yes, he's on as well. Hi, Jesse.
Yep.
Thank you for joining us, and we obviously had the introduction for Jesse already. So what I would like to do is, before we go into questions, I would like each of the panelists to briefly give us a statement what they think in terms of trust in AI and why it is important from their particular perspective. And that's okay, Maria. I would like to start with you.
Of course. Good afternoon, everyone, and thank you for having me here. What an interesting panel and discussion to follow the deep dive Michael walk us through on all things AI. Where do we start when what do we mean by trust in AI? And should we trust AI, knowing that what we've seen so far, AI is yet another technology, while trust as a notion is in fact the fundamental and essential human values that quantify and identify the level of interdependence with one another. Shouldn't we say we need a trustworthy AI that in fact it does what it says on the tin, is actually reliable, delivers an outcome that is aligned with the set of values? I think this is the question that we've been debating and going around in our team in PwC, having the benefit of being a professional services company, not a technology company, and having also the luxury of having, I would say, a more holistic and complete view of the context, economical, social, political, the organizational context where most of the development, the use of AI happens, and what are the implications of this technology. And it's fair to say that the debate around trust in AI or an AI that starts to be manifest itself as trustworthy started when we started seeing the consequences of unethical AI. What does it mean when things go wrong? We've seen in the last 3 years alone, even this year, so many examples when AI actually went wrong. From the famous examples that we've seen over the summer here in UK, with an algorithm that actually was used to predict the A-level results, all the way down to those used in social justice and policies across US and Europe. And with that, an awareness from the civil society, not just from the developers of those technology, on the dangers and the risks that AI brings. And the fact that we are dealing with unique technology that mainly displays some unique characteristic when compared with previous technology, operates increasingly autonomous from human supervision, a large scale, and 24/7. So if we are blessed with this type of technology, with this increased level of autonomy, and the expectation is to behave or display certain behavior, although behavior is intrinsically human, alongside us in the processes, what sort of values that we need to incorporate. And those examples we have seen so far have proven that it's not a default. The values are not incorporated default when we process the data or when we program the algorithms. If anything, it's the default values of the people who actually do the data processing or the software development. And in most of the cases, surprise, surprise, are white men from a certain part of the world. So how do we change that? How do we make sure that the AI does what it says in the team for everyone who is impacted by those solutions? Because another thing that we have learned with AI is that its impact goes well beyond the visible direct users. And look at the most vulnerable group of humans out there, the children. How suddenly, we went from Facebook or Google creating specific products, Facebook for kids, YouTube for kids, for them, but in fact, all of the children, most of the children migrated towards the main YouTube, and with that, them being exposed to a lot of things they shouldn't be exposed. So how do we start incorporating understanding that the implication of the technology we develop are a little bit more profound than anything else we have seen? And how are we able to identify this upfront and then not only identify the values and the norms, but also be able to feed this into the products we're building? And the last thing I wanted to say is that perhaps, Michael or Detlef or others in the course could say, oh, but in A-level, we didn't really use AI, we used algorithms. But we all know that at the heart of the AI are in fact, the algorithms. So if anyone disagrees, is uncomfortable with us using the term AI ethics, maybe we should just talk about the ethics of the algorithms as a beast that seems to be challenging us in so many different levels. And how do we make sure that the algorithms that exist and are used now, and we keep on discovering, like the example with the UK border control algorithm that was discriminating against Black people, to the ones that I mentioned with the A-level, or all the other examples used solely in UK. Let's not go outside UK. We have a way of auditing those so that we identify what is the right outcome that needs to be delivered. And with all those elements put in place, we start seeing not the users and the civil society trusting AI, but trusting the people who are behind AI, that they do a good job. And with that, the AI is trustworthy, delivers what it says on the team. Thank you.
Thank you very much, Maria. Lorna, do you like to go next, please?
Thank you. And thanks so much for the invitation to join today. So I think what I would say very much follows on from the points that Maria has made. I think when I first started working on these issues, the real concerns were around privacy and then a bit later discrimination. And there's a lot of focus on things like data breaches, which is, obviously continues to be a really important issue. But in the last few years, we've really started to see a number of quite negative stories about the design and use of technologies that are falling under this broad umbrella of AI technologies. But really, we're still talking about, fairly basic algorithms and machine learning processes. So we're not sort of yet at the really complicated stages of AI. But we started to see, a number of stories coming out about how the use of these technologies and the design of these technologies has really negatively impacted human rights and society in wider ways. And like Maria, I'm being careful to talk about the design and the deployment and the use because I think the real concerns are around decisions to use these technologies in particular ways rather than saying it's technologies themselves that are the problem. But in the last few years, we've seen a move beyond concerns or building on concerns about privacy and discrimination to really see concerns about the human rights impact of the use of technologies in really key areas of people's lives. So in the public sector, the use of algorithms has been a really big focus. Maria mentioned the use of algorithms in the exams during the summer, but we've also seen concerns about the use of algorithms in relation to determining children at risk, in relation to the criminal justice system. So there's a whole range of ways that these technologies are being used in the public sector, obviously with partnerships with companies, where there's been concerns about really the impact in the areas of our lives that really, really matter. And then, of course, there's been the huge coverage of company and state use of facial recognition technologies, leading to a call for moratoriums in a number of places. And I think when we're thinking about this from a trust perspective, what I think has been interesting and important to take away is that for people, they've often been learning about the very use of these technologies once the stories come out about the negative impact of it. So they haven't often been aware that these technologies might have been used in their lives, their families' lives, other people's lives and decisions about them until these stories have broken. So there hasn't been a lot of transparency, consultation, debate around the place of particular technologies in particular contexts in society, and also not a lot of debate and discussion and actual explanation about the governance and accountability frameworks around them. And from a trust perspective, that can really leave people feeling like AI is being done to them. It's being imposed on them without any kind of real participation, say, in it. And it's being imposed on them in areas that are really crucial for them. And that, I think, can really lead to a diminishing of trust, not only in the place of particular technologies in our lives, but also crucially in the institutions, the companies, the governments that are using them. So there can be a wider knock-on effect around confidence in institutions that work around our lives. And I think that can really mean that the overall trust in institutions and in AI becomes diminished. And the knock-on effect for that is there are many ways in which AI can really benefit our lives and that includes advancing human rights. An area that I work on a lot is in relation to the use of technology for older persons, and we've seen during the COVID-19 pandemic how important a range of technologies have been for older people, and there's also a lot of discussions around whether AI technologies can enable people to live in their houses for longer. But the choices around how AI is designed, how it's deployed, how it's governed will all really affect whether people are willing to buy into the place of these technologies in their lives. And if we continue to see these negative stories where technology is sort of revealed as having been done and had a lot of negative impacts without clear governance frameworks in place, I think there's much less chance of wider societal buy-in and confidence in these technologies, even when these issues are not coming up for them. So there's a bigger knock-on effect for trust and confidence. So maybe just leave it here just now. Thank you.
Thank you very much, Lorna. Mike, you're running a doctoral training center that has trust in the title. What is the relevance from the academic view?
So let me begin by just telling you a little bit about a conversation I had with Chris White, who was the former MP for Leamington and Warwick. And he was working at King's, and he was asking me, when are we all going to be driving around in paper cars? And I didn't understand what he was talking about. And he explained that because all cars are going to be autonomous, they're going to be run by AI, they could be made of paper because they will be much more fuel efficient and they won't crash into each other because we don't need the protection because they're going to be controlled by AI. So everyone's going to be driving around in these AI cars, these autonomous vehicles, and everything's going to be fantastic. Well, from my perspective, that makes no sense because there's always going to be someone wanting to drive a traditional old diesel vehicle that's dangerous and is going to break the whole system. But I think this is the point. We have to design our systems, now I'm speaking from a technical perspective, we have to design our systems in a way that anticipates the dangers. So while I agree with Lorna and Maria about all the things that they're saying, there are also some technical implications for us in terms of what we do here. So, for me, there are two issues. One is safety and one is trust, and they're different. For me, safety is concerned with what we can do technically to provide some guarantees in terms of the systems that we build, that they will do what they were intended to do, that they will do the right thing. Okay? And there are techniques like formal verification, or there are monitoring techniques. So formal verification can prove things. There are monitoring techniques that can try to mitigate the negative effects of any bad actions and so on. There are technical things that we can do, and that's the focus of my Centre for Doctoral Training on Safe and Trusted AI, on the one hand. And then the trust part is about what we, people, humans, need to have confidence in the decisions that these AI systems are taking. And in both of these areas, there are technical things that we can do to try to provide some degree of assurance. And when it comes to trust, it's typically about things like explanation. We want to make sure that the reasoning is transparent and we can understand how particular decisions have come about. So those are both really important technical questions, and we need to design our systems to anticipate bad things happening. That's not to say we can ignore the things that Lorna and Maria have been talking about, because they're absolutely crucial as well. But I'll give you an additional personal perspective, which is I've been working in AI for 30 years or so, and it's never been more popular, more significant, more hyped up than it is now. And so it's really quite an exciting time for me. When I started, we were in what was called AI winter. It was a bad time. People weren't interested in AI. People weren't excited by it. There is a real danger that the benefits that we can get from AI, from the technical things that AI can do for us, there's a real danger that those things will be shoved aside if we aren't able to address these genuine and critical concerns about how AI systems will be used in our societies. And so it's really important that we address both the technical questions and the societal questions, the legal questions, the ethical questions, and the philosophical questions about these things in order to be able to move forward.
Thank you very much, Mike. And Jesse, from your perspective, you already talked about like building kind of restrictions into AI systems. How do you see the level of trust in the systems you work with?
We have techniques already for verification baked into the scientific method. And so when I saw this question, how do we know that AI does the right thing? I first went to, how do we know that science does the right thing? And when we award a Nobel Prize for the discovery of a black hole at the heart of our galaxy, how do we know it's there? And how do we know it's a black hole? And in fact, it's not known that it's a black hole to the accuracy that we'd like. And so that's why you have actually weaselly words in the official Nobel Prize announcement. So we have strategies for verification already in the physical sciences. And we have extraordinary levels of scrutiny on what we do, not just in peer review, but also more internally in the way that scientific data is collected. And so I'm less concerned about, how do I know that what I'm doing in AI is doing the right thing, because I know that I'm going to apply the scrutiny to it. I'm more interested in, is there a way to automate the things that we already do in such a way that I can essentially encode the scientific method or the scientific strategy into the algorithms that we use. For example, issues of ethics or issues of values, what is the counterpoint of those in the physical sciences? What does it mean to have something that's unbiased or less biased? How would I encode that in terms of a physical concept? Because if I can do that translation, then I might be able to figure out, what is the counterpoint of something that's more societally relevant? What's the counterpoint in the things that we're already doing? Something that matters a lot in the physical sciences is the notion of uncertainty, and not just having an answer, but having an uncertainty on that answer. What does uncertainty look like on the ethics side? How do I transmit that there's something that I don't know, which we do all the time in physics? We have data points with error bars, and we teach students a lot about error bars and what they mean. What does that mean if I bring that into technologies at large? So I'm actually excited. I don't have an answer here, but I'm excited to find out, what are the techniques that are currently being done? What are the needs? And can I find a translation to things that we're already doing? Or vice versa, maybe the things that we aren't doing in the sciences. And if we can figure out, broader ethical concerns, what that translation might be in the physical sciences, we may be even to get greater confidence in the results that are coming out of our scientific work.
Thank you, Jesse. So we have already quite a few questions from the audience, so I'd like to pick up some of those. Maria, you said our values are not incorporated by default in AI systems. It's the values of developers. And Lorna, you said that it's important that people understand how these systems are designed and how it might impact their lives. And Mike and Jesse, you talked about kind of differences between safety and implement kind of scientific methods in algorithms. But if we look at how can we engineer trust into systems, how can we engineer ethical principles into systems, and how can we make it open to people who are exposed to AI systems that this has been done? Are there any views of how should we go about building these systems so that we get something that is trustworthy and that is explainable to people, that we have followed certain principles in doing this? Maria, do you want to start on this one?
Yes, thank you. I think that's a very interesting question, and is exactly the right approach. So if we are looking at building this technology, how do we make sure that we have the right values? And what are the right values? And who decides what are the right values? And a lot of debate has been carried in the last 3 years about exactly this topic on how to actually operationalize ethics, what it is that we need to be operationalizing. And we went so far of saying that we need processes and we need checklists and we need training. And of course we need all this, because without proper training of what the value system is and what ethics is, and we know that ethics is privacy and fairness and accountability and robustness and security and safety, all those are key ethical principles. And ethics is also the tension between the trade-off, implementation on more than two principles at a product level will trigger is how do we start making it a state of play rather than a one-off? So let's not fool ourselves, right? The software development happens in an agile manner, while the thinking around ethics is very linear and static. It's almost like a lot of our thinking or approaching the world is a linear mindset, while the world functions very differently than than the linear state. Ethics is very much the same, right? Because it's a reflection of our values. Therefore, doing a checklist at one point in time, you're not going to have an ethical product. And with that, you're not going to achieve the level of trust you're hoping for. We have to start thinking this as a normal state when we develop AI. And it's a shared responsibility. We need not just to achieve transparency. And funny enough, AI acts now like a mirror. I wouldn't say black mirror, although we see things that we don't like, but a mirror that pushes for further transparency. So if you look at our companies, PT, PwC, the Googles, we have become huge system. And because of the complexity of the systems, there's a lot of opaqueness, and with that, the opportunity to hide some practices behind the corporate doors. But AI comes and challenges us to be more transparent. And with that, the need for everyone who's involved, from data scientists to analysts to business owners to executives, to be part of this, the build, to be part of the shared responsibility alongside the development, and understand what's their role in terms of value alignment at each stage. How do they detach themselves from their value? And we know how difficult it is because we bring ourselves to work, and have that conscious process of not codifying their own values, rather than understanding who do we need to represent when we collect the data, when we source data, when we process the data and build the algorithms. So while, as I said, to summarize, is important to have all those different elements and tools that will create the base. I think we have to acknowledge that the only way to have those responsible outcome with AI, responsible, trusted, beneficial to society, is if we achieve a certain state. And that goes back to the culture. You know, fix your culture and you'll have a responsible AI. Until then, everything you'll do will be patches.
Thank you, Maria. Lorna, can we do something from the legal perspective? Do you think it is possible to force AI developers to something that stands up the test of ethics?
Yeah, so I think a lot of the work that's been done around ethics is really critical, and there's been really important discussions around sort of key overarching principles and thinking about how to use these principles as a framing for responsible AI. But I think alongside ethics and the ethical principles, there's obviously the legal part of it. And we already have a lot of responsibilities and obligations under public law, administrative law, international human rights law. And I think from the perspective that we work on, these laws, which are also international standards and norms, are ones that that states and businesses, through the UN Guiding Principles on Business and Human Rights, can really use to work through the risks at the conception, design, deployment phase of AI technologies. And so what I mean by that is, if we're at the very conception and design stage of a particular AI technology, what we're trying to think about at that point are, okay, what are the risks that we can see already with the idea or the design of these technologies? Now, we can be talking about moral risks, we can be talking about societal risks, but we can also be talking about legal and human rights risks. And so risks that I'm thinking about at that stage are, okay, is there a risk of discrimination? Unlawful discrimination? Are there going to be risks to privacy? Are there going to be risks to freedom of expression? If this is deployed in a particular context, like law enforcement, like education, like health, what are the risks to liberty, to freedom of movement, to education as a right, to health as a right, and to life? So at that stage, thinking about the risks, and the way that you figure out the risks are not just with really well-trained data scientists and engineers and people working in the technical sector. It's not just within your company or within your state agency, but it's also with consultation with different groups who might be affected by this. And that's the way that you start to figure out, okay, this technology might impact this in life or human rights in different ways. So at that stage, you're really trying to figure out what are the risks. And doing that with consultation so you really can figure them out in a broad way. And that's what the UN Guiding Principles on Business and Human Rights expect. And it's difficult in this sector because, you know, AI can affect a whole range of stakeholders, but it's doable. And then we're trying to do impact assessments and testing the technology at that time, all to figure out what are the risks and can they be mitigated? Can we put systems in place, like Mike was talking about, to stop these risks materializing? And if we can't, the big question, and it's a growing question, is this a red line? Should we be doing this if we can't protect against these risks? And as I said, the types of risks I'm talking about are these legal risks of things like discrimination. Or does it mean we have to rethink the technology? And of course, you know, I think there's often a tendency to talk about a particular technology, like the contact tracing app and COVID, as one thing rather than a whole range of design options. And I think we're increasingly understanding it is possible to change and modify technology once we go through that. And then when you obviously roll out the technology, because you're not going to be able to predict every risk at the design stage, then when you roll it out, again, it's about having these really good frameworks in place of oversight and accountability, and again, consulting with potentially affected stakeholders to say, are there any new risks, or did the risks we were worried about, have they actually materialized? So it's about that kind of process. And that is the type of process that international human rights law, public law, constitutional law is always thinking about. So it's one that we can easily move over and operationalize here. And it's not about imagining that there will never be risks arising, but it's about putting really good systems in place so that we can actually catch them, hopefully before they materialize, but definitely as they materialize in order to minimize impact. And in that way, then you really start to build trust because there's some really secure system in place thinking about risks rather than just something being thrown into the wild.
Thank you, Lorna. So we have talked about the cultural framework and the legal framework, but let's talk about the perception of these systems. So in people who are exposed to them, how can they trust an AI system? I would like to explore a little bit the difference to other systems that we are used to. Like we step on planes and we trust that the plane won't fall out of the sky, and we take medicine and we trust that it doesn't kill you. So is there a difference or a similarity of trust in these kind of systems and trust in AI, Michael?
So these are difficult questions. Look, I think a useful label for understanding all of these things is algorithmic decision-making. People argue about AI, what it covers, what it isn't, data science, and so on. But algorithmic decision-making covers all of these different areas. And in some ways, the questions are the same. Right? In some ways, what we're doing is we're considering what the implications are of getting it wrong. There are questions of liability. There are questions of how we address this, and so on. The difference with medicine or a plane is that the implications of an AI system doing something based on data that it's been fed that is just incorrect, biased, that leads to inappropriate conclusions, the implications are much more dramatic. They're much more serious, or they could be. And so it's right that the advent of these kinds of data-driven AI systems has brought about a different kind of consideration of how to deal with these technologies. I think we're just at the start of this. So GDPR is one example of a first effort, really, trying to deal with some very basic protections for individuals. and I think that's appropriate, but it's clearly just a first step in our understanding of the wide space that we're working in. So I think we need to move forward carefully. I think the technical questions, I think, are important, and there are a number of these things for us to do. But I will also say something that I think has become much more significant in technical circles, which is, Detlef, you've been asking Lorna and Maria different kinds of questions to the questions that you might ask me or Jesse. There is a recognition now in technical circles that when we train new generations of scientists and engineers, when we train them in the techniques and the tools of AI, let's say, we must also pay attention to methodology and to thinking about responsible research, to thinking about, the questions about values. What does it mean to develop a system that Maria and Lorna have been talking about? What should an engineer be doing? They can't just think about a simple technical solution. They also have to be thinking about what the implication of that solution must be. So there is a merger of all these different things, and I think it's really important there is that merger. But I think it's only happened very recently because of the really significant implications of this particular technology and the reach that it has.
Point. Thanks, Mike. Jesse, what would make you trust an AI system that makes a decision about you?
So I'm really glad that Michael brought up kind of the difference of training. And in hearing what Maria and Lorna were saying, I was saying, if only we could quantify what ethics means, and if we could put a number to it, then I could bake it into my algorithm and optimize it and figure out the trade-offs between different things. If you could put numbers to it, great. But of course, that's not the situation that one is necessarily in. And I think what's challenging for me is that with physical systems, I know what I mean by something that I trust because I have a quantity, I have an uncertainty on that quantity, and I have a methodology that led to that uncertainty that I can scrutinize. And so when we're talking about a risk in a physics context, we are able to turn that into essentially a probability that what I'm seeing in my experimental apparatus might be due to chance versus due to a real physical effect. And in that context, we have such a ridiculously high bar in our field. We use a standard that in other fields of science is enviable. We're able to use 5 sigma confidence for making claims about discoveries in particle physics. But that's never where you are in other contexts, and certainly not where you are when things impact human life, where the uncertainties are much larger. So I wish I had a good answer, but I know that for myself, what I would like to see is attachment to quantities of interest, uncertainties. When I look at polling numbers politically, oftentimes those polling numbers have an error bar on that. And even though people don't necessarily know how to interpret that error bar, at least that information is provided. And so I would feel much more comfortable interacting with an AI system if that AI system said, hey, here's the decision that I recommend, but then here are alternative possibilities, or here are uncertainties on it, something that for someone who's like myself, numerically minded, I can dig my teeth into. I think the challenge is then for people who don't want numbers attached to it, they want more descriptive words attached. How do you then translate an algorithm into descriptive words that carry the same type of information for decision making, but they're nevertheless still rigorous and something that an algorithm could output?
Thank you, Jesse. Any comments from Maria or Lorna?
I was thinking while Jesse and Mike talking that there is something that we need to learn from you, the technologists in the world of AI, which is for the rest of us working in the field is the clear limitation of this technology. I think in the 3 years alone, we have gone through this mystification. It still exists. I think still people not just mystify that the AI is something close to magic, but it is also, we are terrified by it. I think what Lorna was saying, I think we've discussed so much about the risk and the negative effects that will erode the trust and our ability to remain positive and optimistic on how can we innovate, how can we understand what are the benefits and the risk and go together hand in hand. because ultimately most of what humans do have benefits and risk, right? So it's part of how we conduct ourselves as a society. So I think we need to be very careful in not just understanding this clear limitation, understanding where research is going, and plugging it into real life. I think if we are to look at what happens at the technical conferences on those topics, sometimes the practitioners feel like, but we're not really discussing the real issues that we have. So we'll benefit if some of you might focus on some of those topics rather than all of you chasing the same topic that happens at those conferences. And lastly, I think only by understanding honestly the limitation and having this balanced approach, you can then stimulate the collaboration and the collective crunching of what this technology is. Yes, it is novel, right? It's emerging. We are more scared now than we should be. And I don't think we can make good progress if we don't have this balanced view. I think the days of extremes, like either AI is going to kill us or AI is going to change dramatically the world, have gone. I think we have to start being realistic and maintain a sense of optimism, because I think we have enough problems to solve, and they are not rocket science at the moment, and we are sometimes wasting our time talking and philosophizing about things that have not just relevance, but actually dangerous paths. And this philosophication, I can't find the word, should be done by the right people. I think there's too many people debate those topics without having neither the right knowledge or the proper training. So we have to be careful. I don't think that we've seen back in the days where everyone was debating the nuclear energy or brain surgeries, right? So let's listen to the experts and gradually educate others and listen to their opinion as well.
Thank you, Maria. Lorna?
Thanks. Yeah, I think that the point about limitation is really critical. I think what we've often seen in the last few years is either just sort of rolling out of technology, and I think the facial recognition technology has been the one that's really been something that the people have noticed, around let's put it out there without a lot of clear governance frameworks and taking people with them. But at the other end of the extreme, we then see just sort of tech abandonment, where the risks are identified and then there's just no willingness to look at can we use this technology if the right safeguards are put in place. So I think the idea of getting a much more nuanced conversation is really important, and within that, talking about what the limitations are when technology is not ready. I think that's a really important thing to say. We were thinking about this application, but we can't get it right for these reasons. So much more detail around when there's choices to use technology and not use technologies. And I think some of the tech companies have started to talk about, when they are selling technology, when they're not selling technology, and the reasons behind that. And I think that really helps add to the discussion and debate around when it's appropriate. And I think another area is talking about really why do we need the technology in the first place? Why do we want to bring it in? So around, say, the contact tracing apps, what role were they going to play in dealing with the pandemic? I mean, I think that would have been really helpful for people to understand what the place is in a wider public health strategy. So I think a lot of those conversations are really important. The other point I just wanted to make about the airline industry, the question that you asked, Detlef, and around medicines, is I think it's really interesting when you search on the internet for the question about trust and safety of airplanes. What sort of comes up, at least on my first page, were things like you must trust the industry, and then you will feel confident to fly. There's other articles talking about trust in all the different people involved in the airline industry, from designers, engineers, mechanics, pilots, air traffic control. There's a lot of discussion around training, as Jesse and Mike had spoken about, standards, oversight, regulators. So I think what those articles sort of said to me is where people are feeling confident in those industries is because there's this whole ecosystem going on of governance, where everyone is sort of thought about in the chain, and there's a way of regulating it, and that packaged together gives people confidence to get on a plane where they maybe didn't have confidence when airplanes first came around. And I think that that's kind of where we're at with AI technology, that we don't have that sort of good system in place yet for people to feel really confident about it, but that yet they see all these negative stories in quite a lot of detail and a lot of amorphous talk about the promise of AI. So we don't get really good stories about here is a situation where it's really turned people's lives around without causing a lot of risks and a lot of trade-offs where you have to give up some human rights in order to benefit from AI. So I think that that's where we really can learn from other industries around getting that ecosystem in place.
Thank you, Lorna. Okay, I think we are coming to time. I would like to wrap up with one question from the audience, which I think is quite interesting, maybe to have a final thought and a wrap up from each of you. Steve asks, how do we distinguish between AI side effects that are due to training data, where we have insufficient data to train these systems, and effects that just expose limitations around how we define trade-offs on our existing human systems that come from complex political processes and not math? So maybe from each of you, a final thought on trust in AI in this sort of context. Mike, do you want to start?
Sure, and I'll keep it simple. I think it's a hard thing to do. I think trying to work out the source of difficulties is problematic. The way you've posed it, is the problem itself just very, very hard, or have we done a bad job in trying to solve it? And I think the challenge is the challenge that actually we need to pay attention to in general, which is, can we make sure that we have transparency in the way in which these decisions come about? Can we do something to ensure that we can explain what's going on? Because if we can deal with that transparency and that explanation, we don't just provide some indication of why we have not been able to come to a view about something, or why we have come to a view about something in this particular context, but we also address many, many other problems as well. And I think that explanation is something that goes to the heart of many of the challenges that we are facing across all of these different areas. So for me, it's very simple. It's transparency, explanation. Let's make sure that we provide the right information for individuals to have the confidence and the trust in these systems.
Thank you, Michael. Jesse, please.
Well, I think there's something valuable to be learned about how similar questions like this are addressed in the sciences, where, how do you know whether you're really getting the right answer, and how do you know whether you're doing the appropriate trade-offs? And one thing that we do for really high-profile analyses that we do in physics is we do what's called a blind analysis, that the actual data that we're going to make a decision on, we don't allow ourselves to see. And instead, what we do is we create mock simulated universes or mock simulated data sets. And we spend years scrutinizing what happens over thousands or even millions of example data sets to make sure that in all of those test universes, we get an outcome that we think it makes sense. Of course, this raises the question about whether you should trust the simulation itself, so that's a different issue. But it's only when we have confidence on those simulated data sets that then we deploy it on the real data. We say it's called unblinding or opening the box. And it would be very interesting to me to know to what extent that's even feasible with the data sets that are being used in other contexts. In my field, we have the benefit of having trustable generative models to create synthetic data. That's not necessarily available elsewhere, but that gives me at least some pathway forward where both the algorithm for analysis, but then also the algorithm for generation of synthetic data are done together. And if there's a way of doing that in other contexts, I think that's an interesting pathway forward.
Thank you, Jesse. Maria? You're on mute, Maria.
On mute. This is a phrase of two 2020, right? You're on mute. I was reflecting. I think it's a very interesting question. How do you know? You find out, you discover, and you discover by changing the way you work. I think one of the challenges we have in building tech is that we keep solutionizing. The tech sector has been guilty for a while now for techno-solutionism, which is we build a solution and everyone will like it because we say so. I think we have to go back and start framing the problem. So what we're trying to solve, what are the implications of this problem, and what are the implications of a possible solution? And only when we have this correct framing with the correct implication, we then will be able to look at how do we solve the problem on a holistic and end-to-end life cycle. And, there is a fallacy in machine learning community that the fact that the data set is a given. You can't do much about it. But and a lot of the research actually is focusing on that. But what about you start looking at data sourcing and collecting in a different way? And that's when you start seeing the creativity that data scientists are expected to produce. It's not just about crunching data; it's about being creative, solving those problems. So I think we should be starting to educate people on how to frame problems, to be able to have a better chance of understanding the implication of the solution we position, and with that, a response of where are possible sources of harms or negative outcomes will come.
Thank you, Maria. Lorna?
Thanks. So, from a human rights perspective, I tend to start with, well, if I was the person affected by a particular decision, how would I actually go about challenging it? And can I challenge it? Can I know what the basis of the decision was? And can I effectively challenge it? And I think that that's quite a helpful way to look at it, because it then requires you to look at both the AI and the human decision making, because they're relational. And what you're looking for is, well, what is the reason for the decision that's made about you? And what role did the AI, say it was a risk assessment, for example, produced by an algorithm, what role did that play in the decision to give you credit, to not give you credit, whatever the decision was. And I think the question is, how far can you actually get in that, and actually being able to effectively access justice or make a complaint? And if you can't get to the information that kind of helps you effectively understand why that decision was made, then there's a problem. And that might be because no one is willing to give you, because of some kind of proprietary interest, information about how the algorithm performed, what the factors were that it was weighing, what the weighing system even is. It may be that it's too complicated, so it's not possible to explain it. It also may be that you can't actually figure out to what extent was it relied upon or not, and to what extent did they use other evidence in the decision-making process. So for me, really, the question is, from a decision-making, not which one was it, but how was the full decision made? And going back to what Mike was saying around transparency and explainability, how far can you actually understand how all these different components of the decision were reached?
Thank you very much, Lorna. Thank you, all of you. Thank you, Michael, Jesse, Maria, Lorna. I think it was a great panel. We could probably continue for hours on this. And we haven't covered many of the questions that are in the stream here. I think it's AI is a new challenge for us. It's something completely different to planes and medicine, and it doesn't have a pilot, it doesn't have a physician. It's something that's somehow on its own, and we need to figure out how can we build these systems and let them loose on people in the right way, and do this so that they don't cause harm. And probably one of the important lessons is that all of us have to get involved into this discussion. It's very important to have a diverse set of people who look into this, and don't leave it to the engineers, and don't leave it to a small group of engineers to build these systems for the future. Thank you very much again. And to Mike Williams, I'll hand you back the time.
No, Detlef, thank you very much. Fascinating discussion. I'm mostly customer facing for BT. I get questions about AI all the time about, well, can you trust it? So I found this whole thing fascinating from that perspective. So thank you very much. One final bit before I bring this to a close. I want to bring in Simon Perry, who leads on the Tommy Flowers Network and our university program. And he's going to give us just a brief bit. What's next for Tommy Flowers? We've had 5 action-packed days here across a wide range of topics. But what's next? So, Simon, over to you to tell us what's coming next.
So, thanks, Mike. But before we get started, again, I'd just like to echo what you said, Detlef, and everyone on today's panel and all the speakers. Thank you very much. We started off this week promising people 5 days worth of physics and 5 days worth of celebrating physics in our lives. And I think we've really tried, really have delivered that. And I hope that you will have enjoyed it. We've covered everything from optics to quantum to wireless, and we've thrown in a bit of graduate research a day halfway through. And all of the speakers and everyone involved has been absolutely amazing. So really thank you to everyone. And also a really big thank you to all of the backroom team that have made this possible, from our wonderful compare Mike to Fraser Burton, who, as you may or may not know, started the Tommy Flowers Network 4 years or so ago now, so he's now coming back as a conference sponsor, and all of the other people in the team as well. So we've got Nauck, who's helped us massively pull everything together, Sarah McKenzie, who's been our wonderful host and has just been absolutely amazing all week, Carol Fletcher to let us run with it as we saw fit, and hopefully, Carol, you think we've done an amazing job too. And also someone, Nikki Birch, in the background, who helped us in terms of our comms. And because the registrations were so amazing for this event, we had to change presentation platforms, and Nikki helped us really kind of pull this all together. So really big thank you for that. So looking at our next conference, some of you may or may not know, depending on how long you've been on this journey with us, because of the pandemic, we had to cancel our March conference. That was going to be looking at how researchers and research creates value for the economy. And we're going to be looking at success stories, case studies, industry and academic views. We're going to have competition for our PGRs again. So what we're going to be doing in March 2021, and it's going to be the week commencing 22nd of March 2021, is to bring this back, but bring it back in a virtual format. We're going to try and make things work amazingly like we have done this week. So please look out for that. And as this is the first conference that we've run virtually, obviously, as Fraser always kind of points out at the start of every session we run this week, because of the global pandemic, it's caused a lot of issue and a lot of hardship. But something good has come out of that for us. And that's been able to run these sessions virtually and reach a lot more people than we ordinarily wouldn't do. So please come back, and we're going to send out some feedback forms. So if there's anything that we can do better, tell us what you liked, tell us what you didn't like, tell us what was indifferent, because we want to try and make these events bigger and better. And it looks as though we're going to be going virtual for quite some time. So yeah, let us know how we can improve, and we'll take your feedback on board. Finally, I just need to promote, obviously, Tommy Flowers Network. If you're not a member, please sign up. You can look at our blog, https://tommyflowersnetwork.blogspot.com. We've got loads and loads of details on there, the conference material from all of this week, all of the videos, so on and so forth, all of the information on how to actually look at those replays if you missed one of the days will be on there. Also details, again, how to become a member, how to follow us on LinkedIn, all that good stuff. Please just look at that. And also as well, the other thing we do is thought leadership programs, and details of those can be found on there as well. So just take a look when you get 5 minutes. That's great. So I think I do have covered quite a lot in a few minutes, Mike, but I think I've covered what I have to say.
Great. So I thought we were doing one of those lightning talks for a minute from yesterday.
Was it in 5 minutes? I think I kind of covered just under.
Great. No, but thank you very much. That only leaves me to thank all of our panelists and presenters today. But also a big thank you to all of the attendees, because I know this takes time out of people's diaries, and people's diaries are a bit chock-a-block at the moment. So on that note, I'll bring this fifth and final session of this week to a close, and hopefully we will see you all again in March at the next Tommy Flowers Network Conference. Thank you very much.
Cool.